Okay, guys. Oops. Hello? Yeah, good. All right, so we are, welcome back to particle acceleration, part number 2. All right, so we are going to it's an extension of the shock class. And to start with, did I forget to do that? Okay, so the first slide. Hold on. I did. Oh, I don't know. Why is it not working? This guy. Pointer is working. Let me switch to this one here. Okay. So, particle acceleration, again, is very similar than the shocks. It's present everywhere, not just in space physics, but in astronomy. And I think the question, this is in low font, but the main question we would like to understand how they're accelerated, the different populations. So I'm going to show you guys some schematics of the different type of population of particles that exist in space physics. So I'm going to concentrate more on space physics. In astronomy, the particles go to a much higher energy. And I'm just going to show you a little bit the galactic cosmic rays that extend to really high energies. But in terms of populations, I'm going to focus on the space physics. However, the acceleration process should be universal, okay? So although, we're going to talk in a non-relativistic limit. So if you go to astronomy, you would like to extend it in a relativistic fashion, some of the stuff I'm going to say. But we would like to understand how these different population of particles are accelerated. And you will see that there are different mechanisms of acceleration. And it's not clear which one is dominant, okay? And we also would like to understand how they are transported. Because part of, it's a frustration in the field when you work on that you see a spectrum of particles like here. You detect it at a certain spacecraft. And you have to infer where this spectra was accelerated, for example, in a shock, where in the shock, how low in the corona. But you also know that in general, there is kind of hundreds or 200 of solar radii where these particles have to be transported. So which effects happen to these particles as they are transported? So you need to understand that. And there is lots of unknowns that goes into these equations that make this a little bit murky. To come from something like that, a spectrum of intensity and energy, and really pin down the acceleration mechanism, okay? So here is like a schematic of lots of energetic particles in the heliosphere. I'm going to go through the different ones and show you the characteristics. But just for you guys to get familiar with some of the names, we know that, coronal mass ejection, I talked in the morning class, they accelerate particles, flares as well. So we call them solar energetic particles, or SEPs. We also know that you can have co-rotating, interacting regions. I'm going to show more about that. When fast and slow wind interact, can also accelerate particles. When these CIRs, this interaction happen. And as I showed before, you also have the termination shock. It's a gigantic shock that you expected this population, the pickup ions that I just learned, Amitabh talked about it yesterday or 2 days ago. This was expectation that they would be accelerated to MeV or energies, anomalous cosmic rays. What didn't happen? But this is another population of particles that we detect. And finally, Lika talked about that. There are those galactic cosmic rays that enter from the galaxy and enter into our protective bubble, the heliosphere. Okay, so the outline, I thought I'm going through the population of particles, giving you kind of a flavor of what I'm talking. And go through the same thing I did in the morning, do some of my handwriting and go kind of fast as much as I can into the basic of what is a Parker acceleration equation? He has an equation that describes acceleration and transport. And even though we're not going to go through the whole math, giving you a feeling which term is what and what are the unknowns on this equation. And then go in some examples of diffusive shock acceleration. Talk about the effect of parallel and perpendicular shocks, okay? And then if I get to it, I'm not sure, some of the open questions, okay? So population of particles. Before I even go there, I just brought it from the last class because we didn't get to this slide. Remember we talked about perpendicular and parallel shocks? And here is a schematic how in configuration when you have an open field lines form an active region in the sun, you can have, or a CME that is propagating in it, you can have close to the sun a situation where the shock shown here in red can be in a perpendicular situation, okay? And as you go out, the shock can be parallel. So understanding when a shock will be perpendicular or parallel will depend where you are. Okay, the other thing that I didn't get a chance to really talk much, I just wanted to slap really quick a slide, is the fact that when you have, this is a very important question, when you have a CME that will become interplanetary CME called ICMEs, and you're going to have a whole class about it tomorrow, the shock evolves with it, right? Until it reaches us, Earth, and we can detect some particles. So here's an example of a spectrum of particles, intensity versus time. And what we think that depends where you are at the shock, again, if it's a parallel or perpendicular, and if you're attached to the field lines, how the particles will escape the shock and get to you. That issue of transport is very important. So if you are near the nose of the shock, or in a west flank, on the east flank, depending on what the solar magnetic field line is doing with respect to you as an observer, you're going to see a very different spectra. Again, I'm emphasizing, we're going to see more the basic of acceleration of particles, but if you're going to go into the field, those are very interesting questions to really understand. Yes? Intensity of particles versus time. So here you can see there was a CME, so the sun and this, they all, I don't remember the different curves, what are they? That got to be different species, but they all went up, accelerated, and then they rolled down. So time, I think it's got to be hour. But what we're going to see, and this was just a flavor for you to see how the propagating, the transport is important. You can do time, hour, doesn't matter. The CME takes days. And I'm going to show more detailed observations that you will get a better flavor. But one of the things that is interesting that I will try to emphasize in this class, there are certain universal characteristics of acceleration of particles that you can understand that. Why it's falling down, for example. Why it's falling this way, okay? You have a question? No? Okay, so population of particles. So I have a couple of slides more story to show you, and then we'll go to some math. So population of particles, and here is a plot of kinetic energy, MeV per nuc, versus intensity. So what you can see is the solar wind. Particles are around here. And you can see all these different populations. This is oxygen, okay? So in high energy, you're going to get to GeV, a little bit less. You have the galactic cosmic rays. And a little bit less energy, the anomalous cosmic rays. And then you have intensity of particles that come from a solar event, from a shock that propagated in the interplanetary space. And another question we are not even going to discuss is what is called quiet time. This is another very interesting, I don't have a slide on that, but to discuss what happened when nothing's happening in the solar wind is a distribution of particles. You know, if you study distribution of particles, you say, okay, it's a Maxwell-Boltzmann, right? Peaked at the temperature is right here. But you can ask yourself a question, does this Maxwell-Boltzmann in high energy fall to the rock bottom or has a tail? So here I'm showing falling, right? But it might have a longer tail. Another way of saying that, maybe there are so many events happening in the solar wind. Maybe there's turbulence happening at kinetic scales. Maybe there's reconnection happening in the kinetic scales that create those long tails all the time. You don't need an event. And this distribution of particles is never really rock bottom. There are certain people in the field arguing that there are long tails here. So if a CME pass, they're going to take that population of long tail and boost their energy, okay? So it's an interesting topic still discussed here. Okay, so let's start with galactic cosmic rays. If you see the intensity versus energy, and this is known as the largest power spectrum in the sky, it's tung, okay? It's a power spectrum in energy, and around GeV doesn't go as a power spectrum anymore, but what we say roll over. It has this rolling over here, okay? And this is an effect from the heliosphere. So this power spectrum, and I'm going to come back in another slide with the same plot, is seeing in highest energy that probably are accelerated by supernova shocks. Exactly the same mechanism that we think is working in the termination shock, in other shocks. So we are going to see how can you derive a power spectrum. Basically, all what we saw in the morning about shock that has a delta, remember the compression ratio. Once you give me the compression ratio, I will be able to use this Parker equation. It's a simple equation. And you give me the power spectrum, I can the compression ratio, I will be able to derive a power spectrum. So it's very appealing. I assume a shock, you give me the delta, the compression ratio, I can give you a power spectrum. And if you look at galactic cosmic rays, it's a power spectrum that goes from GeV to 10 to the 20 EV. It's a huge range, orders of magnitudes of energy, okay? 10 orders of magnitude of energy is a power law. Those are probably accelerated extragalactic source, some galactic source, some not, but they're supernova shocks. So there's something really appealing that shocks are good accelerators, okay? So this is actually even though the anomalous cosmic rays were not accelerated at the termination shock, people that like acceleration of particles from shocks keep showing this because it's really appealing. You come from the Parker equation, I'm going to show you again, and you just get this power law, okay? So this is a galactic cosmic rays. And like I said, the galactic cosmic rays do not enter easily in the heliosphere. They're GeV, so their mean free pass is on the order of 100 to 200 AUs, astronomical units, but they get affected by the heliosphere. So here's the sun, here's the interstellar medium, and this region here, I'm going to show you a plot about it. It's called the heliosheath. It's where the solar wind is subsonic. Turns out that the heliosheath has a huge influence on how much galactic cosmic rays can enter on that sweet spot of around 1 GeV. So the amount of reduction of that intensity, this is an intensity seen at Earth. We are not detecting all the energetic particles from the galaxy because they're being filtrated by the heliosphere, okay? So right now we left with one of the spacecraft called Voyager 1, we left the heliosphere, so we were able to detect this spectra outside the heliosphere. So it's the first time we have a feeling of how much the heliosheath can, what we say, modulate or filtrate or block the galactic cosmic rays. So it's one data point So this is why I'm saying it's a feeling. It's one data point in one instance right now of filtering the galactic cosmic rays. But it's give us a sense that can be applicable to, as Lika was talking earlier on climate, how much the heliosheath is important in terms of filtering the galactic cosmic rays. And this is a heavy slide. So this is referring to what Lika showed, the galactic cosmic rays, the intensity. So here you can think about intensity, the total integrated intensity of galactic cosmic rays that you see at Earth versus years. And it's vary with the solar cycle. The magnetic field of the sun affects at Earth, this is a measured intensity, of the galactic cosmic rays. In 2004, we started measuring galactic cosmic rays beyond the termination shock in the heliosheath, in that subsonic region. And it went to this level. And now when we cross the heliopause, it's here. So from the bottom line, that the heliosheath is responsible for 75% of blocking the galactic cosmic rays. It's actually way more important, that heliosheath, than that modulation. Now you can also ask yourself how the solar cycle affect the heliosheath. Open questions. But the real spectrum of intensive galactic cosmic rays outside our bubble is here, and inside is right here. 75% we lost. Little bit. Absolutely, yeah. But understanding the physics, I'm just making the point, understanding the physics of the heliosheath. I'm just emphasizing this because it's dear to my heart. But it's a very interesting physics to understand this, and it's important for climate, understanding the shielding of the 75% of the galactic cosmic rays. Open area. Anybody that want to go into it? All right, so this is this part that I talked, this modulation. Anomalous cosmic rays. Anomalous cosmic rays are below the galactic cosmic rays, are here. And this is a composition of them. And they're enhanced in this range, 20 to 300 MeV per nuc. Now, the paradigm in the field was, since 1974, based on the Parker equation that you guys are going to see in a couple of minutes, that you take an energetic population called pickup ions, you get a shock like the termination shock, you give me the strength, and I can give you a power law. I can enhance these particles. Turns out that this paradigm doesn't work. So although the rest of the class I'm going to give you a spiel why shocks accelerate particles, and I'm going to give examples that you do see a spike with the particle going up, and we see lots of them inside the solar system. One of the open questions that I hope you take away from that might be not the whole story, how shocks accelerate particles. Might be other processes playing a role in how particles get their power spectrum. Might be turbulence near the shock, might be reconnection. There is other effects that are also masquerading or helping or not. So just to emphasize again, dear to my heart, that part, anomalous cosmic rays. Again, I'm showing the same thing. This was a paradigm. You go with the solar wind to the termination shock, you take this population of pickup ions and you accelerate it to anomalous cosmic rays. And here is the data. This is a couple of days before the crossing, a couple of days after. Anomalous cosmic rays are here. And if you go before and after, you cannot tell there was a shock. So there are people that love shocks. This is what they do for life. And they will say, look, go back to the galactic cosmic rays. They're such great power spectrum. They have to accelerate particles as well. So they try to invoke that maybe just at the spot that Voyager 1 was not a good accelerator. I think it's a lot of trying to hand wave that this will stand. It's still an open question. There are people like myself that were studying, for example, reconnection. And one of the reasons is if you look at the, sorry for the bad plot here, if you look at the intensity of particle versus time, this dotted line that you barely can see is a termination shock. Not only that the particles did not jump in the termination shock, this is a 2 spacecraft, Voyager 1, Voyager 2, and the different curves are different energies. As the spacecraft travel in the heliosheath, going toward the edge, the spectra keep going up. It's almost like the source is, we're waiting for the source. So when you discuss data like that, you have to revise what I'm going to show you today. It's not just that simple. What I'm going to show you today, the rest of the class, will argue that any shock will jump those particles up. This data is showing that it's not quite, okay? Something in the heliosheath is making those particles keep going up and up as you go further. Okay, so coming back to the other population, I talked about galactic cosmic rays, anomalous cosmic rays. Let's talk about the solar energetic particles. And they come from CMEs, flares, a combination of the two. They can be accelerated by shocks traveling in the solar wind. They can also appear in CIRs when you interact slow and fast wind together, okay? And the CIRs, just to be sure you guys know about that, is the interaction of a slow and a fast stream, and they can produce a pair of shocks, forward and reverse shocks. So the CIRs, again, they're shocks accelerating particles, okay? This is a common theme behind the thinking about how particles get to their energy. One thing I wanted to mention about solar energetic particles, they spend a whole lot of energy. Some of them get to GeV energies. GeV energies are really hard to get to be accelerated. So the thinking is that these SCPs has to be accelerated near the sun when the shock is stronger, okay? Stronger and faster. Again, not proven, but this is the thinking. Okay, so you don't have to read all this. This is just more for myself. I wanted you to focus on this data. You were asking me about time. This is a good data set to look. Here is hours. And what happened around here is CME. This is the energetic particles. We know in a coronagraph in white light that I'm not showing here, a CME showed up, okay? So you know that around here a CME showed up, visible, and those particles jumped up. You correlate this acceleration with CME. There's got to be a shock that was formed and accelerated these particles. And then you're sitting in your spacecraft at Earth, getting the data, and as the hours pass, the intensity is like that, and suddenly there is a peak. Goes down again. And the idea of this peak, that the shock ahead of the CME reach these particles. These particles are relativistic. They run ahead of the shock. So they're messengers. The CME appeared. These particles are running to you to tell you, we were accelerated. The shock is lagging behind. So a couple of hours later, the shock appear and make this intensity go up. Okay? So they are accelerated twice. One at the site and one later on in interplanetary space. So this is a good example how we can tell that there was a shock that accelerated particles right here, okay? Another bunch of examples in my computer which shows a little bit better, but those are lots of interplanetary shocks accelerating particles, okay? So the gist of it, what you would like to get, here is magnetic field, this line, and this is speed, okay? And what you see here it's a shock, this jump, and in the speed, this jump, you know that there is a shock. You have the plasma measurement to tell you there was a shock. And at the same time, there is a peak in the particles. So it's make the point that locally, the shock accelerated particles, okay? And you have lots of these examples. So although in the termination shock, the anomalous cosmic rays were not accelerated, you have all these examples that shocks do accelerate particles, okay? Locally, you have the plasma measurement here, the magnetic field going up, the speed going up, and the particle going simultaneously up, okay? So just, again, I throw this into just to give you a flavor that there is a laundry list of acceleration mechanisms, and we are going to touch in only 2 of them, okay? But you can see the particles that are from KeV. KeV is a little bit higher than the thermal speed of the plasma, going up to GeV or even to TeV, that are accelerated by shocks processes that involve here, you're invoking reconnection. Here you have drifts, you have turbulence, and the scales of this acceleration will be a clue to which mechanism works. Those different mechanisms, we're going to go back to that, require different time scales. So give you a clue what can be the dominant, okay? Okay, coming back to the power law. Let's do the power law again. There is a universality of power laws from galactic cosmic rays that extend for decades in energy to SCPs, we call them, this is a jargon, impulsive. You think there's a reconnection process happening, boom. Particles are accelerated really quickly, and they produce power loss. This is intensity versus energy per nuke. You also see gradual, much slower SCPs that have mostly power loss. They have a rollover, what we call, but mostly power loss, okay? So the question for us, can we explain power loss based on shocks, okay? So we are going to go back to this important equation that have lots of limitations, but does produce a power law, okay? So here's my handwriting notes. So originally it was written by Parker, 65, and you can derive it from first principles, but I'm not going to do here. I have notes if you guys are interested. I taught it in my grad school, and I ended up spending 3 classes deriving that. I was like, too many, so not doing it again. But you can start with the Boltzmann equation. So this is an equation that describes how a distribution function. Here I'm using a capital F or lowercase f. I'm going to interchange. But it's a distribution function of particles evolve in time and in space, okay? Just to, again, put you in context, what we said in the morning was MHD, fluid scale, not kinetic scale, not treating the particles as distribution function, but as a fluid. And we're talking about structure like shocks that has some kinetic physics in it that we're not going into. And now we are going to say those shocks will accelerate particles. So I'm going to go to kinetic physics. And I'm going to slap those 2 together. I'm going to take my kinetic on top of Rankine-Hugoniot and get you a power law. So there are 2 conversations between 2 different approaches in plasma, okay? So this is an equation from Parker wrote, and here is my map, my guide, what those terms are. I think this is the most important stuff for you to get out when you see these equations, if you get a good physical intuition, what they are. So here's the physical, the first part, you're describing how an evolution of a distribution function. So give me a distribution function, how it's evolving in time, and how it's going to evolve spatially, if it's convected by a flow, U. And you have a term here that we're going to come back later that has to do with acceleration. Okay, this is a change. So if you, instead of you glazing over those terms, when you see del F, del P, You're changing energy. You're changing momentum. You're taking a particle that's a certain energy channel and you're boosting it to a higher energy. Okay? So this term tells you that this is acceleration term. Then you have drifts. Drifts come from gradients. Gradients in magnetic fields, okay? And we're not going to go through drifts here, but they can affect the distribution function. And you also have these two terms, and we are not going to focus on this one. We're going to focus on this one that has to do with transport. K, it's where you throw all your lack of knowledge of the system. You say, there is a term called diffusion term K that is here. That tells you how you take a bunch of particles that were accelerated and you bring them to me, how they're transported, okay? So let's go through some simplifications for you guys to get a feeling. So here, let's talk about this. This is 3D, right? One of the assumptions here that I hope I wrote it, yes, Parker assumed it's isotropic. It's a big assumption. There are lots of people trying to extend this equation, and one of the things is to lift this isotropy. Isotropic means that doesn't matter if you're in parallel to the field or perpendicular to the field, the distribution function is the same. And it's really not true when you're starting to look about acceleration mechanisms. So it's a big assumption, but under this assumption, you write this equation that is here. Even though under this assumption, you get to this, it's 3D, complicated tensor. Let's simplify to 1D, okay? Just to get a feeling. And I'm also not going to talk about the acceleration. I'm only going to focus on this term and this term, okay? So I write it like this. Del F del T is del X K. This is my ignorance, my transport coefficient. Del F del X minus V, this is a flow. Sorry, here is U, here is V. It's a flow moving, okay? Del F del X, this is a convection. Example, you're near the sun, you have a flare, boom, reconnection happen, boom, you accelerated particles. You release lots of energetic particles. So it's an impulsive, it's something, boom, happen. You release those energetic particles, and then they will start moving to you, okay? And you solve this equation. So suppose I say, I'm not going to include the convection with the flow, just to begin with. I'm even simplify even more, okay? And I am just going to look at this term, what this term does. So I'm going to solve this equation. It's a diffusion equation. If you remember, diffusion of heat look exactly the same. And you have to have boundary conditions, okay? So I'm going to assume I have a delta function, a spike in a distribution function, okay? This is not delta, the compression ratio of the shock. It's a usual delta, math delta, boom, okay? And you solve this, and you get that the distribution function that starts as a delta will, with time, broaden and fall exponentially. So you have something like that. So at t equals 0, here at Earth, this is me sitting, I had an impulsive event that had everybody concentrated here. With time, it's going to broaden and have this behavior, okay? Now, if I include the fact here, if I include this term here, the fact that the plasma is moving with the flow, I get this distribution function. So this is without acceleration of particles. This is just saying that if I have a certain population of particles of the sun, I let the clock go, the time goes by, and there is a diffusion. It's like diffusion of heat. They are going to slowly diffuse, and the distribution function versus time will look like this, okay? If you look at energetic particles, you see this curve here. This is from simulation from Giorgia Coloni. I took some of this, if you see this blue background of slides from Joe that I stole. And you can see this is in data, also saying this is particles helium flux versus days. And you can see this low, low turnaround. So now we are getting the feeling that this turnaround has to do with diffusion. These particles are diffusing in a plasma that is flowing, okay? So great, they were diffusing. So now at least we understand this kind of behavior. In 2 dimensions, it's much more complicated. So if I have a release in the sun, it's actually, forget the term that has to do with the plasma moving. So I'm just looking here at this term, the K, right? The diffusion. When I wrote it like this, I put 1K. But I can make it a little bit more sophisticated and say K parallel or K perpendicular. And when I talk parallel, I'm mentioning is parallel to the magnetic field line. Perpendicular is perpendicular to the field lines, okay? So I can write it like this. This is without the term of, with the plasma moving and without acceleration. Just taking a source and making it move from the sun parallel to the field or perpendicular to the field. So here I took X and Z, okay? And we are going to come back to that couple of slides. K perp, this is a way you're saying perpendicular, perp. It's hard. As you say, as you know, particles are gyrorading around magnetic field lines. You give a magnetic field lines, particles goes around. For a particle to jump between field lines, it's not easy. It has to have some help from scattering, something has to bring those particles. So we really don't know, neither K-perp, neither K-parallel. There are some theories behind, called quasi-linear theories, that derive the forms of them, but it's an approximation. We really don't know those terms. We do think that K-perp, the ability for particles to jump field lines, it's hard. So the diffusion, K tells you the diffusion, the K perpendicular is much smaller than K parallel, all right? Okay. So in general, this is the case. I just made a note here, even though you cannot read that. This is a note for me to remember to tell you that for galactic cosmic rays, K-perp is very important. For solar energetic particles, not so much. But for galactic cosmic rays, it's very important. I can use a board just for a sec. Because the magnetic field line, so here is the sun. And if you look top down, the magnetic field of the sun, because of the rotation of the sun, far away from the sun, it's like that. It's almost completely azimuthal, okay? Because of the rotation turning the magnetic field line. The galactic cosmic rays come from outside the galaxy, so they're coming perpendicular to those field lines. And they have to get to us. The way that they enter is diffusing with K-perp. So for them, this is a key, how to enter. They have to jump field lines. If they are going to go K-parallel, it will take them forever to get to us, okay? All right. Another plot, people are trying to get what is this ratio between K-perp and K-parallel. So here is the plot I took from this old paper that just shows that people are trying to get, this is a game when trying to look at events and trying to estimate this value. And this person here estimated value that they are pretty high, 0.8, that K-perp for K-parallel for CIRs were on the same order. We would think that K-perpendicular much smaller than K-parallel, but for this was high. So this is an open field. This is just to give you a feeling that when you do codes, for example, that put transport of particles, what you put as K-perp versus K-parallel, it's a free parameter, okay? All right, So it's lots of words. So basically what I want to show here is how particles cross field lines. How do they do that? So here's a simulation with a bunch of field lines. And this is a simulation, again, from Giorgia Coloni, when they follow the particles, and they're trying to see how well those particles jump field lines, okay? And they're trying to, this is K-perp per energy. They take those simulations, those are particle simulations, try to estimate what is K-perp, okay? So what they do, they will do from scattering, from drifts. Maybe the magnetic field lines are not straight lines, they meander. Some kind of a turbulence have to kick those particles between one field line to the next, okay? Jokipi and Parker did lots of work about it. And here's Giacoloni and Jokipi, this is this figure from them. Okay, so we saw, so far what we talked in the Parker equation, let me go back, are this diffusion term that make the spectrum turn. And we talked about this convection with the flow. We haven't talked about this term yet, okay? We're not going to talk about the drifts here, but we didn't talk about this term. So this term here is the energy change. This is where the acceleration of particles lies. You're bringing the particles and you're making them move in energy, okay? So if you have a distribution function, instead of the distribution be like that, you're making them gain energy, okay? You're moving particles and they gain energy, okay? So we are going to talk now in the next couple of slides about how shocks do that. Can we derive a power law? Let's see about time, how we're doing. I go until 3. Let's go for a couple of more slides and then we do a break, okay? So shock acceleration. So now it's interesting. This is a funny game when we go back to what we saw in the morning, fluids, shocks, and we are going to slap on top of it the Parker equation that is a kinetic equation, okay? So you're going back to the shock physics, and you're saying there is an upstream speed and a downstream speed. Sounds familiar? And we're also going to say, just to make our life interesting, we're not going to go much about it, but just for you guys to get an intuition, there could be some disturbances on this nice ordered field. Can be some meandering here, some turbulence, okay? And now the shock is going to compress the magnetic field line. Got a question? No? And it's also going to compress any turbulence. It's going to make the downstream turbulence stronger, okay? So delta B2, the delta here is not the ratio, it's just the jumping B, is going to be stronger downstream because of shocks. So I am going to have particles here. So suppose I have a distribution of particles hitting with the solar wind that will go through a shock and will get accelerated. They can also cross a shock and get scattered by this turbulence and come back. Depending which shock it is, if it's a perpendicular shock, they're going to be going through the shock, surfing the shock, gaining energy. But at the same time, they can also go back and forth like ping pong rackets, gaining more and more energy. This could be quite complicated. We're going to start ignoring those turbulence for now and just say, give me a shock, beautiful condition, laminar flow, quiet, and see what happens, okay? So before I go do that, there will be this other aspect that I'm going to come back to that of acceleration time. How quickly can I accelerate the particles? And it will depend on the diffusion coefficient. because it will depend how quickly the particles come back to the shock to gain more energy. Or suppose that they diffuse so quickly, they just see the shock once and goodbye. But maybe their mean free path is so short that they get scattered, they get a kick in their tush, and come back to the shock and get accelerated further. So it's important to know the diffusion coefficient, okay? At a perpendicular shock, you have this electric field. Because the magnetic field is perpendicular to U. U is going this way, magnetic field is this way. You have an electric field that is going to accelerate those particles along the shock. So a particle, even without diffusion, can stay at the shock and get accelerated to really high energy. So we will come back to that, but this to give you a flavor that perpendicular shocks can be very different than parallel shocks. Parallel shock have a magnetic field this way. The particle is going to gyro radii along the magnetic field and cross the shock. So just to make my point clear here, I see some confused faces. If I don't have turbulence here, I will have a magnetic field for a parallel shock with a shock here, right? It's parallel to the normal. I have the particles gyro radii on the magnetic field. They say, hello, shock, and continue. They get one chance to get accelerated. If there are fluctuations on the other side of the shock, they have a chance to come back and get further accelerated. Okay? For a perpendicular shock, it's very different because the magnetic field is like that. So if a particle gyro radii here, for some reason, managed to get scattered here, or just this or even without it, just this magnetic field get convected through the shock, it's going to have lots of time to get accelerated. So the acceleration we will see happen much quicker in a perpendicular shock and to much higher energies, okay? So the perpendicular shock will take advantage of this electric field, and again, this K-perp is less than K-parallel. It's harder for particle to scattered, okay? So this is called shock drift acceleration, and Rob Decker did an amazing paper in '88, and here is a picture from a simulation that he has done showing a perpendicular shock. This is energy. Look how neat this figure. This is energy versus space. The shock is right here, the dashed line. And he's following a particle. The particle is here. It's get transported, get to the shock, and use the electric field of the shock, the perpendicular shock, and gain energy. Gain energy until it escapes the shock upstream. Another particle gain energy and then escape downstream. But you can see that those particles, this is 3 different particles, are gaining. Here is like 1 time their energy. In this case, he managed to make them move almost to 4 times their original energy. Okay? The perpendicular shocks are really good accelerators. And what we're going to do next, after the break, is to take the Parker equation and derive the power law. This is called diffusive shock acceleration. Okay, so let's take a 5 minutes break before we dive into this. Hello. Oh, it has a delay until it's come. Okay, so let's go to the shock acceleration part. I'm going to go back to my notes. I hope it's not too small for you guys to see. What I'm doing is taking the Parker equation in 1D, okay? So maybe you need a reminder of the Parker equation. Taking this gigantic equation, again, taking away the drift, I'm not dealing with this, and I'm writing all this in 1D. And I'm also dealing with one K here. There is no K parallel, not K perp, just K, okay? All right, so I'm asking the question, what happened when you transport particles through a shock? This is a question we're asking. So you have a shock with an upstream conditions, B1, K1, B2, K2, okay? And I am having U1 here and U2 downstream. Okay, so here is a Parker equation, and I'm going to do it in a parallel fashion. B1 is along U1, okay? So I'm going to write it in 1D. So I'm writing in 1D. You have the diffusion term, the convection with the flow U, and the acceleration term, okay? And the question I'm asking, in steady state, so in del F del T goes to 0, what is the effect of the shock on F, okay? Due to transport and due to the compression of the flow and what's not that the shock does, okay? So here's my condition. U is U1 in upstream, so I am putting my coordinate system here. So X negative is this way and X positive that way. And I do U1 and U2. And I'm going to include the fact that these particles can diffuse in space. So I have a K1, a diffusion coefficient, and K2. The diffusion probably downstream, the shock is different. There's probably more turbulence. K2 gotta be bigger than K1, okay? So I have these two terms. What do I need to solve this equation, guys? What's the first thing you need when you solve any equation? Start with a B. Boundary conditions, exactly. So I couldn't hear you. Maybe it was that. Boundary conditions. So my boundary conditions are that far away from the shock, going this direction, I have 0 distribution function, very little, okay? And as the distribution function is going to go through the shock, it's going to get a finite number, okay? The other constraint that upstream and downstream, the distribution function should be continuous, matching at the shock, okay? So I'm solving the Parker equation in region 1 and 2, and I'm going to match at the shock. So in region 1, upstream, this is my Parker equation when I dropped the time dependence, and I'm not going to deal upstream. I don't have shock, so I don't have to deal with this, okay? So upstream, I have those terms only equal to 0. And I get this solution that F1 is A1 of P exponential U1 K diffusion plus B1 of P. In region 2, I'm far away from the shock. I don't have to deal with acceleration either. So the acceleration terms goes away. So I have the same equation here, and I get the same solution, but with different coefficients, A2 and B2, okay? So now I'm going to apply the boundary conditions. As I'm going to go far away upstream from the shock, the distribution function should go to 0. And if you go to this equation, you take x to minus infinity, you find out that B1 should go to 0. So B1 goes to 0. Okay? Now, as I go far away from downstream, I need to have finite value. So I will need that A2 will go to 0 because there is an x here. X will go to infinity. This whole thing is going to explode. So I need to set this to 0. Okay? So I get that B1 goes to 0 and A2 goes to 0. I can send you guys this talk if you want to go through the math. Yes? Because I didn't upload it in time. So, yeah, what? I'm going to assume it's insignificant. It's very small. You can put a finite value if you want. But you could. You could. I'm simplifying. It doesn't have to really go to 0. I'm simplifying, saying most of the acceleration, most of the distribution will be at the shock. So I am assuming it's going to 0. OK, so then I get f. This is my f distribution function. And later, I think Nick is going to tell me how to send this talk to you guys. I don't know how. But you can go through the math. You get this expression. And this is how it's look like. The f versus x, you have, depending on the energy p, you have a term a of p. I didn't determine what is a of p is. OK? Depending on your momentum, you're going to have an increase as you get close to the shock, and then to a finite value. This is what you get from the Parker equation. And this increase depends on the diffusion. It's called E-folding distance. OK? Depend on your diffusion coefficient, how this goes. I have some slide that I cut that in the Voyager data, you can see the particles E-folding doing that. It's really nice before the shock. But you can see that in the data, the particles don't increase the intensity like that very nicely. OK. What is this A of P, guys? Just to be sure you guys are following. Let's go back here. What is missing in this equation? Parker equation, diffusion, transport. What is missing here? No. So Parker equation, we had a term for transport, convection with the flow, and another one was what? No, there's no collisions here. Acceleration. Acceleration of the shock. I solved this Parker equation far away from the shock when this term was not important, and also downstream, upstream and downstream, where I didn't have to include the acceleration term. OK? So I'm getting this constant A of P that I'm going to determine by looking what the shock is going to do. OK? So far, this is just for you guys to follow. So far, this is my distribution function far away from the shock. Now I'm going to try to determine what is A of P. So I'm going to take the Parker equation and take a little epsilon just before and after the shock, right? So I'm going to ignore now. So I'm going to just around the shock, and then I'm going to force epsilon to go to 0, just at the shock. I am not looking at the microphysics of the shock. I don't care. I'm saying if the Rankine-Hugoniot conditions are valid, what a shock is going to do for my distribution function. So I do that. Here is my full Parker equation, but now I'm putting the acceleration term. It's important because I'm at the shock. So I solve that, and I integrate in x just before, just after the shock, OK? And what I get when I do epsilon going to 0 is So now I have all these terms. I have to take this term, the diffusion, this term, and do this integration in x, right? So this term, the first term, I take from minus epsilon to epsilon, I get this result. And as I take epsilon goes to 0, I get some A over U1, OK? Now I'm going to take the second term and integrate between minus epsilon to epsilon. And what I get is these two terms that as epsilon goes to 0 is 0. So the second term doesn't contribute anything. The third term, that is the acceleration one, will give you this. If you integrate, what you're going to see, you get u2 minus u1 del this constant, no constant, this function a of p over the natural log of p. So I add all these different terms, and I get this is a Parker equation at the shock. And the result is that A is a constant A naught. Sorry, it's small. I should make it bigger. P over P naught to a power of gamma. And gamma here is a compression ratio. It's related with the compression ratio at the shock. Because I'm getting, if you look here, let me write it back here for people that cannot see in the back. What I'm getting, my result is by integrating the Parker equation at the shock, that this A of P, this thing that appeared in the distribution function, vary with the momentum as 3u1 over u2 minus u1. So it's a very nice result. I just took the Parker equation, and I found out that A of P, I can write it up as A is A naught, P over P naught, to this gamma that is related. So gamma is 3r over r minus 1, where r is u1 over u2. R is what I did before, the delta, the compression ratio. So isn't it nice? I took a kinetic distribution equation, Parker. And so just to recap, I took this equation in 1D. I had a shock. I solved it far away from the equation without acceleration term, upstream, downstream, and then I solved at the shock, and I get this term. I have more stuff that will come in the distribution function that depend on how strong is this shock, this gamma. So the overall spectra, if I go back here, far from the shock, what we found that f of x of p, so f of x of p is this A. And after the shock is E, or before the shock, E1 x k1. This is for x less than the shock. After the shock is just this. So look what happened. Look how cool. I derived that the distribution function, it has this E folding, right? I have the shock, right? And the particle goes up. This is in time, right? To different energies, I have a different E-folding that depend on the diffusion coefficient. But how the intensity, how the distribution function is going to behave in different energies will be as a power law. And the power law depends just on the compression ratio of the shock. It's pretty amazing. I just did fluid before, after the shock. I don't know the physics of the shock. I just know the strength. And I can tell you that if the Parker equation is correct, the distribution function after the shock will be a power law. And this index of the power law depends only on the compression ratio of the shock. Okay? And before I have this diffusion, I really don't know what it is. So we go back to the power law spectrum. I see galactic cosmic rays with a power law. I see SCPs with a power law. People look at that, and they can get the power spectrum, and they feel good about that because shocks, we just saw that shocks, that ubiquitous. You take the Parker equation, and you get power laws. Other question? What? Oh, this is just an initial energy. Okay? It's a normalization. Okay? So before, this is a power spectrum that is going to be accelerated by the shock. Before it's going to be modulated, this is a result of the shock. This is what you're going to see is a rise to this value. Yes? The power law. No. It's going to behave like this. Right, yeah. Oh, I see what you mean. Yes, yes, it's going to be. Modulated by the diffusion. Okay, so what is the effect? So far, we talked in general in shocks, but what is the effect of the fact that shocks can be parallel or perpendicular? Okay? So those are slides that I borrowed from Giorgio Coloni talking about this acceleration time. And this has to do with physics I'm not going to cover. You can look at this reference that gives you the acceleration time that depends on this diffusion coefficient. And the physics behind it is how quickly I can bring a particle back to the shock to get further accelerated. It's not just crossing one time the shock. So it turns out that you can show that this is an expression of the acceleration time. But again, what I said before, I don't have a whole lot of time, so I just want to hit a couple of points. That again, because the perpendicular diffusion is much less than the parallel, the acceleration time is faster. Just look here. The acceleration time depends on the diffusion coefficient. If you're in a perpendicular shock, when K perp is small, the acceleration time is smaller. It's faster to accelerate particles. So bottom line, what you can show based on data, but the theory agree that you can have for a parallel shock an acceleration times of days. It's really long. Why for perpendicular shock, it's hours. We saw those distribution functions jumping on amount of hours. So you want an acceleration of hours, not days. Now, the couple of aspects that I do want to touch is what do you do with a parallel shock? Parallel shock is what I drew here, that you have the magnetic field line parallel to the shock, and you are crossing one time the shock. So the way to bring the particles back and get further accelerated is by waves or some turbulence downstream. Turns out that you can show that there are waves self-excited, that if you have a distribution function, you can have kinetic processes that create waves downstream. Those waves will scatter the particles back to the shock. So you don't need to invoke waves. They are naturally created. So this is good. But still, the conclusion is from simulations that acceleration at a parallel shock is unlikely. So we do look for perpendicular shocks to accelerate to really high energies, okay? So GeV, the bottom line that the energetic particles, the solar events that get to really high energy, probably are accelerated at perpendicular shocks. So you need to look at perpendicular shocks near the sun. Some open questions really quick. You look at papers. There is one famous here by David Lario in 2003. He looked at lots and lots of interplanetary shocks and found that most of them do not have enhancement of energetic particles. So why is that? Not all shocks accelerate particles. I also told you about the termination shock. Not all shocks, like termination shock, accelerate particles. So there are people extending. The beauty of the Parker equation that we just took a very simple Parker equation, we derive a power law. So if you want to invoke other mechanisms like reconnection, turbulence, you need to extend the Parker equation to include those mechanisms, okay? Those mechanisms usually don't keep the distribution function isotropic. So the Parker equation relies on the distribution function being isotropic. So extending the Parker equation to be anisotropic is also complicated, okay? We had a work in the Heliophysics on trying to say, I'm not going to go through that, I'm showing here that the reconnection between field lines in the heliosheets could produce power loss. We were able to produce anomalous cosmic rays. But was basically following contraction of magnetic islands in reconnection to create those power loss. And if you try to do some analytics to follow that, it depends how long the particles stay in those magnetic islands before they escape. It's messy. But I wanted just to finish this class to tell you one of the future avenues in acceleration of particles might be how to incorporate these other processes to explain events like the one in David Lario, the anomalous cosmic rays, that show that not always shock accelerate particles. Okay? This is what I have to show you. Cool. And I did on time. Questions? Well, so this mechanism, the way we did it, this is particular to this mechanism, okay? We were studying in the heliosheath. You had opposite magnetic field lines. You have what we call sector regions, opposite magnetic field lines for a long time. So these plots show plus, minus, plus, minus, plus, minus of opposite field lines. And then you create lots of magnetic islands that contract. Now, there are instabilities that maybe Amitabh talked, fire hose instabilities, that can shut off the amount of reconnection. So the particles start bouncing back and forth from the islands until the reconnection, until the instability shut off the reconnection. And it's affect differently electrons and ions, and it's affect them differently depending on their energy. Because it depends how many times they bounce. It's a Fermi mechanism. And ultimately also depend on the volume, how many islands you have to jump. And you can see here that in this case, the most energetic particles gain most of the energy. This is in the ions. And here too, the electrons. This is in different times. So earlier in time, this is a spectrum, and this high energy gained a lot of energy. The low energy particles didn't gain much energy. Okay? So it's affected both electron and ions, that the amount of energy gain depended on the energy. See what? Single? Yes, yes, yes. So I don't have a slide here, but there are groups that are invoking turbulence downstream of the shock, or the fact that the shock is maybe not planar, just like a sheath, but maybe undulated. To have favorite sites of turbulence, favorite sites of reconnection. No. So all the Parker equation that I showed, we did not invoke reconnection. And we had a power law. Accelerated. Yes. Oh, because this is, we did not include the magnetic field here. And we just said, suppose, it's almost like I did a parallel, right? It was a parallel without turbulence. I did B along U, and I went upstream, downstream, what the compression of the shock will do. Parallel. Right, so I just showed, so one encounter with a shock, it's producing power law. I did not include it in terms of multiple scattering. So it depends on the orientation of the magnetic field line. So it's, if the normal, if B is a long normal, it's parallel. If it's B perpendicular, it's a perpendicular shock. But it's encountering the shock multiple times. Right. Any other question? No? The same as parallel shocks. It's a form of, you have a disturbance moving, for example, faster than the magnetosonic speed, and you form a shock. But the magnetic field is perpendicular to the normal, so you have a perpendicular shock. Yeah. So the production of the shock is a fluid production. So this, I'm going to form a perpendicular shock independent of what the particles are doing. It's just a fluid moving faster than the magnetosonic speed, and I form the shock. Now I'm asking the question, particles, as a test particles, I'm not influencing the plasma. If they are sitting on the field lines being convected with the flows, they're going to cross the shock. So they're going to start being accelerated. They have to jump, yes. So this, I had a slide really quick when I showed. It might be some scattering. Some scattering needs to, it's a K-perp. Is that what I'm hiding in the K-perp? Oh, good. Oh, she was asking if reconnection is going to help the particles jump field lines and go through the shock. This hasn't been studied much, but you're mostly invoking turbulence of scattering, making those particles jump. Any other question? Well done.